This talk is on ozone monitoring, and it focuses on the details about how scientists monitor the ozone layer. But before we get into that, there's three reasons why we might want to monitor ozone. The first one is to actually monitor the depletion of ozone in the ozone layer. That helps us make something called the UV index forecast to determine how much UV exposure people will be exposed to on particular times. And very importantly, to monitor the progress of the agreements and decisions that have been put in place to reduce CFCs, e.g. the Montreal Protocol, to see if they're having any impact on the restoration of the ozone layer. Before we look at how they monitor, and there's monitoring in three different ways, before we look at that, we have to look at how we actually monitor. What are the units of monitoring ozone? And the units are something called the Dobson unit. And one Dobson unit is equivalent to a pure ozone layer 0.01 millimeters thick if it was at 100 kilopascals and 0 degrees Celsius. So if we got all the ozone and brought it down to sea level, one Dobson unit is equivalent to 0.01 millimeters of pure ozone at sea level. And the usual concentration of ozone in the ozone layer is only 300 DU, which is equivalent to 3 millimeters of ozone. So the ozone layer, as you can probably realize, is very fragile and something we need to take care of. But in terms of the three ways of monitoring ozone, the first one is something called a Dobson spectrophotometer. Spectrophotometer. And this is a ground-based instrument. There's a picture of one. If assume this works, I can drag up here. It's basically a ground-based instrument, computer-controlled, which looks into the sky above it and can figure out the ozone concentration in the sky above the spectrometer. And there's one drawn on the picture here. So how does it work? It works by monitoring radiation from the sun. Now we know the radiation from the sun comes in all different wavelengths, and what the Dobson spectrophotometer looks at, it looks at two radiations, two UV light radiations very close to each other. It monitors one that ozone doesn't block very well, and so that radiation would be coming from the sun. That radiation that ozone doesn't block would get to the Dobson spectrophotometer. It then looks at another UV spectrum, one that ozone does block very well. And so when that radiation reaches the ozone layer from the sun, not much gets through. And how much gets through depends on how much ozone there is in the atmosphere above the spectrophotometer. So there's a lot of ozone in the atmosphere. Those concentrations of these two wavelengths, their concentrations will be very different. If there's not much ozone at all, their concentrations will be very similar. So by comparing those two concentrations of light coming through, or intensities of light coming through, it can determine the concentration of ozone in the sky above it. And while it's very accurate, the limitation is it's only for that one place on the Earth. So it's only for local measurements of ozone. But even still, many of these devices are spaced all over the world, and they give very quick and rapid indications of the ozone content in the sky above many different places around the world. The second way of monitoring ozone is with weather balloons. And there's a few pictures here if we can have a quick look. The weather balloon itself looks like that. It's one being released from either the Arctic or the Antarctic, I'm not sure. The weather balloon itself is this here. This is the actual helium-filled balloon which takes it up into the sky. The instruments are carried on this little device down here, and we can have a look at one of those. Should be a second picture. It's a device, it's called a sonde. I think that's how you pronounce it. I'll probably pronounce that wrong. That's the device that actually measures the ozone concentration in the atmosphere as the weather balloon rises up into the atmosphere. So the scientists who use these devices release their weather balloons, and the weather balloon slowly makes its way up into the atmosphere. And while it's rising up into the atmosphere, it's recording its altitude and also the ozone concentration at particular altitudes. And you get graphs looking something like this. So the Dobson spectrophotometer we looked at over here just tells you how much ozone there is above the spectrophotometer in a particular point on Earth's surface. The balloon, though, can record the ozone concentration changing with altitude. And so in the troposphere, the ozone is quite small. By the time it gets to the stratosphere, there's a rather large peak in ozone, which then falls back again. So that's a nice way of monitoring the actual ozone concentration at different altitudes. The problem with weather balloons, once again, they're local, and their actual path is weather controlled. Where they actually end up depends on the wind. And so there's two ways of monitoring ozone. The Australian Bureau of Meteorology, BOM, uses both those methods to monitor ozone. The third method is satellite monitoring. And there's been a range of satellites over a number of years monitoring the ozone layer. First was Nimbus, the Nimbus satellite. And then there was a device on a satellite called TOMS, which is the Total Ozone Mapping Spectrometer. Recently, there was something called the OMI instrument, which is on the AURA satellite, which is called the Ozone Monitoring Instrument. But the one that's being used right now, which was launched last year, is something called the OMPS, the OMPS, which is the Ozone Mapper Profiler Suite. And it's carried aboard the Suomi NPP satellite. And here's an amazing drawing of a satellite just here representing our satellite-borne ozone monitoring instrument. How these work is similar to the Dobson spectrophotometer, but what they look at is wavelengths of light that ozone scatters back into space. So as light strikes the ozone layer, certain wavelengths or certain frequencies of that light are very well scattered by ozone, and so what these satellites do is they measure the light reflected or scattered off the ozone layer to determine the thickness of the ozone layer. And why this is called an Ozone Mapper Profiler Suite is because this particular satellite can actually record a profile of the thickness of the ozone layer at different altitudes and where the ozone actually is. And it's from these sort of satellites that we get these global pictures of ozone concentration. These are the very famous typical pictures of maps of the ozone layer where it's showing you the actual thickness of ozone at different spaces all across the Earth's surface. So one advantage of these satellite-based systems is they're not limited to local areas, they are actually a global monitoring. Unfortunately, though, obviously you've got to launch a satellite, so they're actually quite expensive, and not every country can launch their own satellite to monitor ozone, but the data from these satellites is shared through different organisations throughout the world. How they monitor the entire globe is because they're polar satellites. And what that means is the satellite is actually orbiting from north to south pole. And it does that quite quickly. Every 100 minutes it does one orbit. So it achieves approximately 14 orbits per day, but as it's orbiting, the Earth is spinning underneath it. So it can actually monitor the entire globe over a number of days. So these are very accurate and very useful ways of monitoring ozone concentration in the atmosphere. So in summary, we've got Dobson spectrophotometers on the ground, weather balloons which are launched into the atmosphere, and satellite monitoring which monitors the ozone across the globe.